Good evening everyone. My topic is random search algorithm. In this, we compare a current good solution with a randomly chosen competitor. If the competitor is better, then it becomes the current good solution. When we terminate the search, the solution we choose is the one that has been visited most often. The steps are as follows. Initialize counter variables c of I equals to 0 for I equals to 1 to up to k values. Suppose we have the k possible solutions, then select an initial solution I0 and set C of I0 equals to 1, where C of I counts the number of times we visit solution I. In the next step, choose another solution I from the set of all solutions except I0 in such a way that each solution has an equal chance of being selected. In the next step, run simulation experiments at two solutions, that is first solution I0 and one more solution I dash, to obtain the outputs of y of I0 and y of I dash. If output performance of y of I dash is less than y of I0, then set I0 equals to I dash. In the next step, increment the counter value, that is set C of I0 equals to C of I0 plus 1. If it is not done, then again go back to step 2. If it is done, then select as the estimated optimal solution xi star such that C of I star is the largest count. That means it is for minimization. For minimization, every time checking for lesser value. For maximization, run simulation experiments at two solutions I0 and I dash to obtain outputs y of I0 and y of I dash. If y of I dash is greater than y of I0, then set I0 equals to I dash. Let's see the example. Suppose a manufacturing system consists of 4 stations in series. The 0th station always has raw materials available, where the 0th station means where we have 4 stations, that means 0, 1, 2 and 3. When the 0th station completes work on a part, it passes the part along to the first station. Then the first station passes to the second and so on. Buffer space between stations 0 and 1, 1 and 2 and 3, 2 and 3 is limited to 50 parts total. Buffer space is nothing but where we can store raw materials. If say station 2 finishes a part but there is no buffer space available in front of station 3, then station 2 is blocked, meaning that it cannot do any further work. The question is how to allocate these 50 spaces to minimize the expected cycle time per part over one shift. Let's see the solution. Let xi be the number of buffer spaces in front of station I. The decision variables are x1, x2, x3 with a constraint that x1 plus x2 plus x3 equals to 50, where the buffer space between station 0 and 1, that is x1, between 1 and 2 buffer space is x2, between 2 and 3 buffer space is denoted as x3, where as given in the question, buffer space between stations are limited to 50 parts total. Therefore, x1 plus x2 plus x3 equals to 50. To simplify the presentation of the random search algorithm, let the counter for the solution x1, x2, x3 be denoted as C of x1, x2, x3. The steps are as follows. First step, as we seen in the algorithm, initialize counter variables C of x1, x2, x3 equals to 0, 1 for each possible solutions x1, x2, x3. Select an initial solution randomly. x1 equals to 20, x2 equals to 15, x3 equals to 15. x2 equals to 15, x3 equals to 15, where these x1, x2, x3 equals to 50, and set counter value of this solution 20, 15, 15 equals to 1. In the next step, choose another solution from the set of all solutions except 20, 15, 15 in such a way that each solution has an equal chance of being selected. So take 11, 35 and 4. Run simulation experiments at two solutions to obtain estimate of expected cycle time, that is output performance of 20 15 15 and output performance of y of 11 35 4. Suppose that y of 20 15 15 is lesser than y of 11 34 4, then the solution 20 15 15 remains as the current good solution. Then in the next step, increment the counter value to 1. Then again go back to step 2. Choose another solution from the set of all solutions except solution 20 15 15 in such a way that the solution has an equal chance of being selected. So take 28, 12 and 10. So next step is to run simulation experiments at two solutions to obtain estimates of expected cycle time y of 20 15 15 and y of 28 12 10. Suppose that y of 28 12 10 is less than y of 20 15 15, then the solution 28 12 10 remains as the current good solution. So then increment the counter value of this solution, that is C of 28 12 10 equals to C of 28 12 10 plus 1. So this procedure continues. When the search is terminated, we select the solution x1 x2 x3 that gives the largest counter value. So for example, choose another solution from the set of all solutions except 28 12 10 in such a way that each solution has an equal chance of being selected. So take 0 14 and 36. Compare 0 14 36 with 28 12 and 10. If solution 28 12 10 is better than 0 14 36, then increment the counter value. So then the solution of the counter value of 28 12 10 becomes 2. So one which has the largest counter value, then that is the best solution for the given problem. Thank you.